Okay, hello everyone. Nice to meet you. My name is Takumi from University of Tsukuba. Today, I'm pleased to present my research topics in here, Tsukuba, because I'm living here and I came here by just walking, about 20 minutes or something. But today, I wanted to introduce some restaurant or some good scenery in Tsukuba. But today I came here to present my research topics, which is toward QoL, quality of life improvement of ALS, which stands for amyotrophic lateral sclerosis patients in terms of developing of the full-body P300-based tactile brain-computer interface. Takumi Kodama, and my professor is from University of Tsukuba as well. But my main professor is Tomaszu M. Rutkowski. He is a Polish and he is affiliated with the University of Tokyo. So actually my research is done most of in the Tokyo, not in Tsukuba. Sorry. So let's begin with some introduction about BCI. Have you ever heard about BCI? Okay, some of them. BCI is a new technology, and this interface can exploit user intentions only using brain waves. Please look at this diagram. This is actually brain-computer interface. Brain-computer interface can capture human brain waves on the scalp with the small electrodes. I used 8 electrodes on the scalp, and these signals will be processed in the signal processing section in brain-computer interface, and then these processed signals will be converted to feature vectors, and these feature vectors are input to the classifier, which is very common classifier algorithm, and then classifier algorithm translate the human intention by just brain waves, and then the BCI can send any command from human intention to the robot. This is an example I will show you later. Okay, so let's move on to the description of ALS patients. Like I said, ALS stands for amyotrophic lateral sclerosis, who have difficulty to move their muscle, so they have difficulty to say something or to tell their intention with muscle movement. So BCI, which does not require to use any muscle movement or something, so it could be communicating tool for ALS patients. He is Dr. Hawkins, most famous ALS patient in the world, probably. So there are many research approach in this study BCI, but I chose the tactile P300 BCI paradigm as my research topics. This P300 BCI based BCI paradigm can predict users' intentions with finding P300 responses like shown here, and these responses actually are captured from human brain waves. And to evoke these P300 brain responses, we gave vibration stimulus to human skin and some certain of areas. So I will show you the example. Please look at these figures. At first, like I said, I used the vibrotactile stimulus small exciters, just emitting some vibration. Small vibration stimulus, boom or something, and then attach just example, we attach small vibrotactile exciter to both hands, and we associate these vibrotactile exciters to just example Japanese tea or orange juice. Of course, this subject attached the electrodes on the scalp, and this subject cannot use their muscle and say something. And just we associate that if you want to drink the Japanese tea, please concentrate to the right hand stimulus. And another example is if you want to drink orange juice, you have to concentrate on the left hand stimulus. And we gave the vibration stimulus randomly, like right, left, or something. And then usually after the experiment, after the experiment, we can confirm P300 responses where the subjects are concentrated on. Do you understand? So in this example, we compare the brain waves when the right-hand stimulus are coming or the left-hand stimulus are coming. Actually, this subject concentrate on right-hand stimulus and all ignore for left-hand stimulus. And then we can analyze their brain waves after the experiment. This is actually the average of 50 times stimulus or something. Because it's an example. So we can confirm this kind of P300 responses in his brain waves. And then finally, these brain waves will be converted to future vectors. And finally, classification algorithm, machine learning classifier, translate his intentions just as a probability. Like I said, this subject chose right-hand stimulus, and P300 responses are showing up. The machine learning algorithm classifies their intention as 92% for the Japanese tea and 43% for the orange juice. This is a small example, and my research purpose is developing a new tactile, this kind of BCI paradigm which uses biotactile stimulus. And we propose new communication option toward ALS patients for improving their quality of life. So let's move on to my research stuff. My approach is full-body tactile P300-based BCI. We call it FBBCI. We applied, the example was just 2, but we applied 6 biotactile stimulus patterns to user's back. Please look at right pictures. We put the small biotactile exciters to 6 locations on subject's back. And during the experiment, subjects may discriminate their differences of vibration patterns. And then subjects can use FBBCI just with their body laying down. So it could be applicable for spinal cord injury patients and some disabled people. So this is our example, and this is actually BCI user. He can control. He can use BCI, and his intention will be converted to BCI, and this small human robot will move in. I will show you some example. This is demonstration movie, and like I said, this is a FBBCI user. And we put actually 8 small exciters on the Japanese style mattress, but we create 6 biotactile stimulus patterns from 8 exciters. And then robot will be moving. During the experiment, like I said, this subject concentrate one of the 6 biotactile stimulus. If he successfully tell and discriminate this biotactile stimulus, the robot will be moving. So this robot also has 6 commands. These 6 commands are associated to 6 FBBCI commands. So like you see, the robot, I think next is command number 4. If subject can successfully choose the command number 4, which is located on the hip, the robot will going back. And then also the stimulation pattern number 6 and number 5 is associated to left leg, and robot will be sitting. And finally, if the subject can successfully choose number 6 stimulus, which is associated to right leg, and robot will be shaking his hand. Okay, this is double speed. Okay, I will skip. Yeah. So this is FBBCI specification. This system's master is a personal computer, like you see, because I'm a computer science student. And this computer that operates full of the BCI system. For example, the computer sends the operation, sends a command to give the vibrotactile stimulus during the experiment. And the subject feels the vibration stimulus. And then his brain waves will be captured by his scalps. And the right figure shows the BCI systems. And like I said, there are 8 electrodes to attach to his scalp. And his brain waves will be processed. The bandpass filtering and downsampling, which is actually common signal processing process. And after the signal processing, these brain signals will be concatenated to create future vectors. And these future vectors are inputted to the classifier, which I chose nonlinear SVM with Gaussian filter. And then a classifier algorithm translate his intention, and then this BCI send a command to robot to control him. So I will give you detailed description about the signal and signal machine learning process. And the brain waves which captured by human scalp is we call it actually this is EEG, but we call it event-related potential, ERP interval. The which ERP interval will be it's captured 800 milliseconds long, just after the vibrotactile stimulus onset. But we conducted this experiment at the 512 Hertz in experiments. So these waves consist of numerous plots, and these plots will be converted to the future vectors later. And okay, I will give you the experiment. Actually, before converting the vectors, we computed to signal processing to brain waves, both bandpass filtering and downsampling. By using bandpass filtering, we deny some signal noises, and then by doing downsampling, we can compress the vector length, and we can stabilize the signals. Then after the finishing the signal processing process, these 8 electrode signals will be concatenated to create feature vectors to input classifier. So, and then I chose the classifier algorithm for SVM, which is a Gaussian kernel nonlinear SVM, and then to train the classifier, this is 2 classification, and we put target stimulus pattern brain signals, and then and likewise we put also the non-target, which should not be confirmed P300 responses within these brain waves. And we input both target and non-target stimulus pattern brain signals and future vectors to train classifier. And then finally, in the test experiment, to confirm the P300 responses are existing in the brain waves or not, we evaluate the classifier, and finally this BCI system understands human intentions or not. So we conducted experiments for 10 subjects. The mean age was 21.9 years old, and we conducted 1 training experiment and 5 test experiments for each subject, for each of the 10 subjects. And I chose 40 Hertz for the stimulus frequency of exciter, vibrotactile stimulus exciters, and GUSB amps, active electrode EEG system, was employed to capture EEG signals, and sampling rate was 512, and vibration stimulus length was set at 100, just 100 milliseconds long. And ISI, this stands for the interstimulus interval, is a duration between each stimulus, is set at 400 to 430 milliseconds.
You have 5 minutes.
Okay. This is example. Like you see, this is successful, very successful example. We could confirm the P300 responses all of the 8 electrodes to attach scalps. This name shows the human scalp area, and we can confirm that this purple line that means when the target vibrotactile stimulus patterns are given to the subject, and blue is non-target. And we could confirm P300 responses in all electrodes. And also, we calculate the classification accuracy. This rate shows how much classifier can correctly translate human intention with brain-computer interface. The mean average of each 10 subjects was resulted in 59.83%. This is relatively good. This is relatively good results in the tactile brain-computer interface study. Like you see, some of the subject number 9, the average rate was 93.33% or something. And also this experiment, the chance level. This means this is actually 6 commands-based BCI paradigm. So 1 divided 6 is 60.67%. So we could calculate the much better average than the 60.67%. So I would say this is successful experiment. So let me conclude my research project. The effectiveness of FBBCI modality was confirmed. In terms of classification accuracy, it's by far than the 60 points, which is a chance level. And we can expect to improve QoL for ALS patients. But however, I think the obviously more analysis would be required because we conducted just only 10 healthy people, not actual spinal cord injury and ALS patients. So we need more study for practical applications. So these are publications which related to this experiment and this research project. Thank you for listening. Would you have any questions or comments?
Any question?
Yes.
Please inform your name and your opinion.
Okay, my name is Muhammad Asaduddin. I'm from Kais. I've also worked with EEG before, and I was wondering that when you do the bandpass filtering, you do bandpass filtering, but you are looking for a response from your stimulus. So there is possibility that the bandpass filtering actually filters out the response that you are actually looking for. So when you do the bandpass filtering, you might actually filter out the response that you are actually looking for.
I want to find that. Okay.
Yeah. So yeah, that's the first comment. So that might be the reason why you have lower accuracy than you are expecting. And then the second one is that the fibrotactile impulse, have it ever been fired simultaneously? And have you ever? Not yet. Yeah. So I was wondering that if you fire the fibrotactile at least 2 or more simultaneously, then you might have a different map for your CBI, BCI, BCI. Yeah.
Okay, thanks for the comment. I would answer for the first question. I took the bandpass filtering just beginning of the BCI, but this is actually bandpass filtering is between 0.1 to 30 Hz. This will not kill the potential which I'm looking for, because this kind of the P300 potential is very strong. This is the result was just averaging all of the experiment and all of the subject. So this is actually potential is around 0 to 5 microvolt. But when we find the P300 responses during the experiment, this signals, this potential reaches around 20 or 30. So it is enough to capture and it is enough to find P300 responses with the bandpass filtering between 0.1 to 30 Hz. Thanks for the comment.
In addition to his comment, actually there is a BCI paradigm. The name is SSSCP that recognize simultaneous tactile stimulus for some kind of communication. Okay. Is there any comment? Then we will move to the third speaker.